Okay, so in this podcast slash video, we will be going over trig functions and trig identities. Now, the first thing we need to know in order to be able to understand trig identities and trig functions is to understand the unit circle and the new measuring system in pre-calculus 12, which is the introduction to radians. Now, let's start with the unit circle. So, the unit circle is a circle with a radius of 1 unit, and it's centered at the coordinate 0, 0, being the origin of the xy graph. And there's a couple little details about this unit circle that we need to go over. At any time when we take a particular part out of the circle, no matter how big the part is on the outside, the round part, we call that the arc. Now, after we have an arc, if we draw 2 lines straight to the origin, it'll give us an angle in between. And that angle is known as the central angle. And that whole piece that kind of looks like a piece of pizza is known as a sector. And at any time, just to review, just in case no one somehow forgets this, is at any time when we draw a line from the origin to the outskirts of the circle, that's known as a radius. Now let's go over what a radian is. A radian is the angle inside that little piece of pizza when the arc length is equal to the radius. So when the arc length is equal to 1 radius, we have the angle within will be 1 radian. There is a formula that relates the arc length to the radius and to the angle inside. Arc length will always equal the angle theta, which is the angle inside, times the radius. So in this example, we have an angle at 2.36 radians and a radius of 10. So when we multiply them together, we get the arc length. So the next thing we're gonna learn is the term coterminal angle. Now, a coterminal angle is pretty much any way you can get to the same position on the 360 degrees that you have on this graph. Like, for example, right here, we have an angle at 55 degrees. Now, we want to be able to get back to that same angle, but not with the angle 55 degrees. So let's say we're already at angle 55 degrees. Every time we would add a 360 degrees or subtract a 360 degree, we would end up at the same place as we were before. Now that's all those angles that will end up leaving us with the same terminal arm in the same position are known as coterminal angles. Okay, so let's go over the CAS rule. The CAS rule pretty much splits up the x and y graph into 4 sections or 4 quadrants, as we know from before. So let's go over what this means. So on the bottom right of the circle, this section, you can see that it says C and it stands for cos. This just means that in that sector, whenever we have a terminal arm that ends in that section, or we have an angle in that section, the cosine value of that angle will always be positive. When we move up, any cosine, sine, or tangent ratio in the top right quadrant will always be positive, and moving to the left, top left, any sine ratio of an angle on the top left will always be positive, and on the bottom, same thing, but with the tangent. Now, this is useful when we have to solve trigonometric ratios, and these are all problems that we faced in pre-calculus 11. Now, we're just replacing our normal 360 degree scale with the radian measure, and the problem will be solved the same way. So for example, let's say we are given a triangle, a right triangle with a hypotenuse of 3 centimeters, a leg that has the value of x, and we're supposed to solve for theta. Now, theta in this specific triangle is the opposite from x, and as if we can recall from pre-calculus 11, our abbreviation for how we can use these different sort of trigonometric ratios and which sort of problems. So the abbreviation, as you may remember, is SOHCAHTOA, and that stands for sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tan is opposite over adjacent. Now in this triangle that I'm talking about right now, as I mentioned before, the side that we don't know, that we're trying to solve for, being x, is opposite from theta, and we have a hypotenuse of 3 centimeters. Now the question has given you theta equals 0.73 radians. Now all you would do, like before, we would set up the problem as sine theta equals x over 3, which is opposite over hypotenuse, and then we would plug 0.73 as our theta value. Then we would use algebra to solve for the rest. We would times both sides by 3. We would punch 3 sine 0.73 into a calculator, and we would get a value of 2.00 centimeters. And that's pretty much how we solve all problems that we faced in pre-calculus 11 with the new radian measure. Now, this podcast is kind of challenging for the audience as well as me, because you will have to imagine these sort of problems, some of them that I will be trying to explain. Now, let's talk about how the CAS rules comes into hand with some of these problems. So let's say the question is giving you a coordinate and you're supposed to solve for theta. How you would go about that is you would locate the point. For example, let's say the point is 3, 2, which means your x value is 3 and a y value of 2. As you can imagine, that point will be in the first quadrant, which is the top right quadrant, which states that all trigonometric ratios will have a positive value in this example. Now, if you go through the problem and you get to theta by using your inverse trigonometric ratios and you somehow end up with a negative number, you can go back and recheck your work, because you would know that there's something wrong, because all trigonometric ratios would have to be positive in the first quadrant. With any sort of problem in this chapter, the first thing that I learned that we have to do is locate which quadrant the angle is in. Figure out which other quadrants the angle could be in for the trigonometric ratio to still be true. Look at the question and see. First of all, look at the question and see if there's any restrictions of what the angle can be, and if there's not, with the help of the CAS rule, locate which quadrant it will actually have to be in for the trigonometric ratio to be true, and then go through and use algebra and inverse trig ratios to solve for whatever the question is asking you to do. Okay, now let's go over what the sine, cosine, and tangent graphs look like with the radian measurement. Okay, so here's a graph of sine x, and as you can tell, it kind of looks familiar, as you might have seen the same graph in physics or chemistry classes, as this is the same graph as a sine wave, and pretty much any sort of wave kind of has the same type of look. Now let's go over some of the properties of the graph. As you can see, the graph peaks at every pi measurement. So it starts at 3 pi over 2, then pi over 2, then if you were to go further, it would again peak at another pi. After you add another pi, that means that the graph has a period of pi. It repeats itself every pi radians. the properties of the graph, like its period, its amplitude, they will all change if the sine function was to be transformed by adding coefficients and stuff like that. We already went over this different sort of transformations that happen to a graph. Now this becomes the main topic of how all this video and this podcast is leading to, of all of the trigonometric ratios, functions, and graphs, all leading to sound waves and how they come in sound engineering and production, and how musicians and producers use sine functions and cosine functions pretty much on a daily basis. Now, let's continue to go over the other graphs. Okay, so here's a graph of the cosine function. As you can see, it looks extremely similar to the sine function, and if you were to pay close attention to it, all it is a sine function, but moved to the left. In the sine function, the graph would cross the x-axis at every pi, as you could see before. Now it crosses it at every pi over at pi over 2, and then at negative pi over 2, then negative 3 pi over 2. So it is kind of just shifted to the left a bit. The sine function, it would start at 0, 0. If you would ignore all the negative x values, the sine function would start at 0. But the cos function, it starts at 0, 1 instead of 0, 0. If you were to ignore all of the negative x values. So that just goes to show again that the graph is just a little bit moved to the left. That is how the cos function graph pretty much looks, and it's just it's a transformed version of the sine graph. Okay, here is a picture of what the tan graph looks like in radians, and as you can see, it looks extremely different than the sine and cosine graphs. It's kind of like the odd one out between the trigonometric ratios. As you can see, there's a vertical asymptote at every pi, starting from negative 3 pi over 2, and then negative pi over 2, then pi over 2, then 3 pi over 2. That is one of the reasons why the graph looks so much different, because x cannot equal negative pi over 2 and negative 3 pi over 2, or pi over 2 or 3 pi over 2. If you were to plug in those values into your calculator for the tan ratio, you would get an error, which means those are restricted values, which is why the graph looks the way it does, because of the restricted values within the tan function. Additionally, if we can remember, at all of these asymptotes, there's a particular end behavior. They're all pointing to the opposite sides of the y-axis, which clues at the fact that the asymptotes have odd multiplicity, and that is why one of them is going all the way up and one of them is going all the way down. Okay, now that we have all that information in our back pocket, let's go over what an identity is. And identity is not what we're talking about, human identity. We're talking about in trigonometric ratios and functions, or any sort of function for that matter. So no matter what function you have, let's just imagine this. You have a squared minus b squared is equal to a plus b times a minus b. And that's, hopefully you remember, that's the difference of squares. And just keep that in your head. And let's go over what an identity is. So an identity is when no matter what value of a and b we put in, both sides of that function will equal the same. So in your head, let's say we have a is equal to 1 and b is equal to 1. So a squared, which means 1 squared, minus b squared, which is 1 squared again. So 1 minus 1 is equal to 0. Now, so our left hand side is equal to 0. Now let's move to the right hand side, which was a plus b times a minus b. So if our a is 1 and our b is 1, a plus b is equal to 1, and a minus b is equal to 0. Now 1 times 0 is 0 again, which is I can prove that, in fact, that function is an identity. Now, that's one of the methods that we're going to learn that you're going to use to prove identities, is to just plug in the value, see what the left hand and the right hand side equal, and prove if it is identity or not. Now, that can go for any sort of trigonometry function. So let's rewind back to when we were talking about our sine and cosine graph. So as we said, the cosine graph is just the sine graph but translated to the left, right? I mean translated to the right. And so what that means is that sine x is equal to cos x minus however units it has been translated. And if we were to go back and look at the graph, the cosine function is moved pi over 2 units to the right, which then we can come up with our function as sine pi or sine x is equal to cosine x minus pi over 2. Now let's see if that is actually a identity. If you were to plug in any sort of value for pi or for x, which is the same thing for in this, let's say our variable is x in this situation. No matter what value you put in for x, the equality will always be true and there will be no restricted values. So therefore that is in fact an actual identity. As we were going through the trigonometric ratios and functions unit, we derived a couple different trig identities, which ultimately was given to us on a formula sheet for quizzes and exams, and that really helped us to understand these identities way more if we were to just be given these identities on a formula sheet without any sort of explanation or trial and error on how they were actually derived. Here's a list of all of them, and it would take a couple more podcasts and a couple more videos to go over each one, but this was given to us during exams and quizzes, and we also learned how to derive them. So there's a couple different methods in which we are able to prove trigonometric identities. The first one is substitution. So let's look at an example right here. So we have to prove that secant x is equal to tan x times cosecant x. Now, the method that we were introduced to during the year was that split up the function into two sides. Secant x will be a left-hand side, and tan x cosecant x will be the right-hand side. Now, this was applied to every single sort of problem we got, and how we would go about solving this would be to identify which side is most likely the most complicated one and just go right for it. Let's simplify the most complicated one and see if we can get it to equal secant x, and if we are able to do that, we can prove that the identity is truly an identity. Now, our first method, as I said, was substitution. So as we look at the right hand side, which we identified as being the most complicated one, we can see that tan x and cosecant x have an identity within the identity formula sheet. Tan x is equal to sine x over cos x. So we're going to go ahead and plug that instead of tan x. And cosecant x is the reciprocal of sine x, therefore we can plug in cosecant as 1 over sine x. And now on the right hand side we have sine x over cos x times 1 over sine x. And as you can see, that can be further simplified by canceling out the sine x's on our top and bottom of our fraction, and we're just left with 1 over cos x, which as you know, 1 over cos x is equal to secant x, which is the reciprocal identity. So we just proved the identity using substitution. Another method of how we can prove an identity is if we ever run into a complex fraction, we have to be able to clear it. Pretty much what that means is, let's say for example, we have tan x divided by secant x. And if we were to substitute in our reciprocal identities and our trig identities into tan x and secant x, we would be left with sin x divided by cos x divided by 1 over cos x. That is an example of a complex fraction. Now, as you can see, the way we simplify that is we multiply the denominator by the reciprocal. We multiply the numerator by the reciprocal of the denominator. So in this example, we multiply sin x divided by cos x. We multiply it by reciprocal of 1 over cos x, which is cos x. And that just simplifies the denominator and numerator, which is cos x, and we're just left with sin x. And if we were lucky enough and the question gave us sin x on the left hand side, we would have just proven the identity. Another situation we might run into is having to either factor or distribute a trigonometric ratio in order to move forward in attempting to solve our identity. Let's say we have on the left hand side of our function cosecant x of 1 plus sine x. And on the right hand side we have 1 plus cosecant x. Now, the way we would go about doing this is we would have to remember that we can distribute cosecant x as it is being multiplied by 1 plus sine x. So then we would be left with cosecant x plus cosecant x times sine x. Now we would go back to our substitution method and substitute in the reciprocal identity of cosecant x, which is 1 over sine x. And now we can see that our sine x's cancel each other out and we're just left with 1. And as you can see now, on the left hand side we just have cosecant x plus 1, which is equal to our right hand side, which is again another way we just proved an identity. Another situation we might run into is if we have to rationalize a numerator or denominator by multiplying by the conjugate. So let's say we have sine x over 1 plus cos x is equal to 1 minus cos x sine x. So let's say we decide to start with the left hand side. We would multiply the whole left hand side by 1 minus cos x over 1 minus cos x, which is the conjugate of 1 plus cos x. And that is a method we learned in grade in pre-calculus 11 on how we can simplify and rationalize denominator and numerators. So after that we would be left with sine x minus sine x cos x on the top and 1 minus cos squared x on the bottom. And if we look at our identity sheet, 1 minus cos squared x is equal to sine squared x. So on the top, now we have sine x minus sine x minus sine x times cos x, and on the bottom we have sine squared x. Now we can go back into the method we talked about previously, which is our factoring or distributive method, and we can see that both terms on the numerator of our left hand side have sine x at the moment. So we can pull that sine x out, so we're left with sine x times 1 minus cos x. Now, as you can see, we can simplify the denominator and numerator at the moment because we have sine squared x on the bottom and sine x on the top. So we can simplify, we can take off 1 sine x from the top and 1 from the bottom and be left with 1 minus cos x over sine x, which happens to be equal to our right hand side. So we have again proven another identity. Now, that brings us to the end of the material we have to go over in the trigonometric ratios and identities chapter. But now comes the fun part of me relating this whole chapter to my personal hobby and interest and what I want to pursue as a career, being music production, audio engineering, and sound design. Now, how does that relate to trigonometric ratios and identities? Well, I did not realize how related they were until one day when I was working in my music production application, which is FL Studio, and I was inputting different drums and sounds into the application to come out with different ideas of patterns and just music I wanted to create. I inputted this kick drum, and the cool thing about this application is that it shows a visual of what that sound wave of that certain sound that you just inputted to the application looks like. So I'm going to show a screenshot of it right now. As you can see, this kick drum's visual sound wave looks exactly like a sine or cosine graph, which is not far from what we talked about earlier, as I said that you may have seen a sine graph in physics or chemistry when you went over waves and sound waves. Now, how more can we relate this to the pre-calculus 12 curriculum? I noticed that whenever I was manipulating sounds within the application, whether it was changing the tempo, whether it was stretching the sound, because in this application, which is FL Studio, by just should mention that. Yeah, in FL Studio, you're able to stretch out whatever sound you inputted. It has that. You have the option to stretch or compress the sounds that you have. Now, that pretty much is it's transforming the sound wave of that certain sound, which in reality is transforming the graph of it, which in reality is changing the equation of that sound pretty much. Let's say, so if you have a kick drum, and if you were to transform it and manipulate it to make it sound longer, the sound wave would look extremely, it would look way bigger. It would look like it is longer in length, which would cause it to not have sort of that kick that you're used to hearing in music. Which, what you're doing to it pretty much is you're changing the period, you're making the period way longer, which is why you won't hear a certain boom, you will hear a certain, it would be a really long sound wave, and it won't sound exactly like it did before. So that's just one way of how musicians and producers manipulate their sound waves to make it sound like they want it to sound. So another example of that is, let's say you have a hi-hat drum, and it sounds extremely broad. It's not as tight as you would like it to sound. And most modern music today has hi-hats in it that are very tight. They're not very stretched out. So in order for you to make sure it is as tight as you want it in the application, or any sort of music making application, you have to be able to manipulate the sound to make it sound tighter. And again, that's the same as transforming the graph as we do in pre-calculus 12. So I always did that whenever I was using this application. I just did it by heart and never really thought about how we were doing the exact same things when we were going through transformations and sine and trig identities and stuff like that. So that just goes to show that it's like, as you can see, we went over a lot of different topics we talked about in this chapter, but that sort of basics of trigonometry and identities and functions and graphs is applicable to such a big industry, which is music and music production, music engineering. Just that sort of basics graphs of a sine function and a cosine function, and transforming the graph, manipulating the graph, therefore manipulating the sound. All of that is the basics of music production. Without that, there would be no different sounds. Without that, there would be no differentiation between different sounds. All sounds with the music would sound exactly the same, and we would have no music, and I would not have the hobby that I love today, and I would not be pursuing what I want to do today if it wasn't for trigonometry and ratio and sines and cosines and tangents, which is crazy to think about, because as you go through these topics throughout the year, you're kind of like, when am I ever going to use these type of things? But if you look at the bigger picture, it is applicable in such a big part of our lives, no matter what you're trying to do. And yeah, that brings us to an end of this podcast / video. Hope you enjoyed. Check out the rest of the artifacts.